morning.
Yeah. In French.
Good morning, everybody. It's a pleasure to have Nahid Emad with us today. She's a professor at the University of Paris-Saclay Versailles and affiliated to Maison de la Simulation and Lee Paradal laboratories, where she leads the intensive numerical computation group. She has been scientific director of 20 PhD and HDR and has authored more than 150 articles in international journals, conferences, and book chapters. Her main research interests are in numerical algorithms, linear algebra, parallel and distributed programming methodology, software engineering, for parallel and distributed numerical computing, and big data analytics. And it's truly a pleasure to have you here today with us to talk about high-performance learning with a unite and conquer approach. Welcome.
Thank you very much, Eva. So I have to precise about my laboratories that, I am affiliated to two laboratories. One is in computer science, and the other one is computational science. That means so many applications that this is the reason somewhat the reason that I am affiliated, because I work on many applications also. So this presentation, the objective of the presentation is to highlight the interactions between HPC, linear algebra, and machine learning methods. So, there is, I suppose that all of these very large models in deep learning, and especially the models transformers. You have here a chain of transformer, and I can say that in many machine learning methods, we have many linear algebra algorithms. But for example, here we have in this part and in this part where we have the embedding input and output, we have many linear algebra problems to solve. So when I speak about linear algebra problem, it's not just the operation on matrices. It's a little more, and we will see what is about that. So, in machine learning methods, we have especially two problems. One of them is linear transformations, and the other one is the system of linear equation. So linear transformation is about eigenvalue problem. I hope that you know what is eigenvalue problem. And the other one is the resolution of a linear system. So, when you have a set of a data set A, which represents a set of observations, and a vector Y, which represents the labels associated with this set of observation. So the relationship between the data set and the labels can be expressed by a linear system of equations. So, this is one of the problem in linear algebra, one of the important problem in linear algebra. And the other problem, the linear transformation, is about eigenvalue problem. So I would like to focus especially on eigenvalue problem. For the moment, I would like to say that when we have a set of in matrix of eigenvectors of a data set, what is important to know that this set of eigenvectors define a very important basis of the space. And the importance of this basis is that when you apply the matrix on this set of eigenvectors, we have nothing changed concerning the orientation of these vectors. So, you know, for example, if the vectors are here, in the very simple case of matrix 2 by 2 matrix, you know, if you apply the matrix A on these eigenvectors, nothing change concerning the orientation of these vectors. So I suppose that you have you know a little what is principal component analysis. You know this technique is used very intensively in machine learning, but we have to know that this technique is just an eigenproblem technique. You know, we will see after, but what is interesting with this eigenproblem technique that it can be applied to dataset where dataset is represented by a matrix, square matrix, or by a rectangular dataset. So the problem is that to use this kind of linear algebra problem, as the dataset are very, very large size, we can't make use of numerical method, you know, classical numerical method to solve them. So we need to high performance techniques, but before applying high performance techniques, we need to use the adapted numerical method to solve this kind of problem, large problem, and after applying HPC techniques to this adapted numerical algorithm. So that means we need to define some special programming models, and when we look at carefully on this kind of programming models, we see that we are obliged to define the new numerical methods. We can't use the classical numerical methods in the context of very large problem. So what I would like to say here is that we have to see the convergence between big data analysis and HPC to define new and smart methods. So in this context, I would like to present this talk by according to these points. That means to see in the first the relationship between linear algebra and numerical and machine learning method, and after I would like to introduce an innovative unite and conquer method, and show how this method is this kind of method are very well adapted to this kind of architectures. So I would like to speak about also a framework to use this kind of modern numerical method for machine learning, and we will see some examples in clustering and cybersecurity. So just a rapid look at the machine learning method. You know that the objective as indicated here, the objective of machine learning method, and this is a short classification of machine learning method, and we see that, for example, for supervised machine learning, we see here, for example, for the linear regression, we have linear systems. And we have for recommendation systems, we have eigenproblem. For unsupervised, we have the reduction of dimension. And essentially, this kind of machine learning, or essentially eigenproblem and the larger general case of eigenproblem, which is SVD, singular value decomposition. And also we have affair with the Markovian decision problem in the case of reinforcement learning, which is in very general, very often, which is eigenproblem. So I would like here to present which are the main problem in linear algebra. So the first problem, we have just two main problems in linear algebra: linear system and eigenproblem. So linear system is a problem that is well mastered. Many people worked on linear system, and there is many methods, very well defined method for linear system. But this is not the case of eigenproblem. And one of the reasons is that we haven't many applications for eigenproblem before the events of internet. With social network, little by little, we had many problems, many applications with eigenproblem. And one of the first application, it's Google search. When you use Google search, there is the PageRank underlying algorithm, which is eigenproblem. So, for a linear system, we can make use of iterative method as we can make use of direct method. But this is not the case of eigenproblem. For eigenproblem, we are obliged to make use of iterative method, even if the size of the matrix are small. Even if we have just a small or moderate size eigenproblem to solve. So for this reason, I would like to focus on eigenproblem and iterative method. So I would like to repeat again that the importance of the eigenvectors. Here I have a very small matrix. Here it's one of its eigenvector, and here is any vector, just vector 1, 1. We can see that if we apply this matrix to this vector, this is the multiplication of this matrix by this vector, we have this kind of situation. That means this application scale the vector, but doesn't change the orientation of this vector. But if we apply the matrix A on this vector, we have this situation. This vector is 1, 1, but is not the same orientation when we apply the matrix A to this vector, and we have this situation. We have scaled the vector, but also we change the orientation. This is a very important property of the eigenvector that is used in machine learning. So our problem is we would like to solve eigenproblem. I am always on the context of linear algebra. So I would like to solve eigenproblem for very large and sparse eigenproblem. That means the matrix is large size and very sparse. So we understood that we have to use iterative methods. When we use iterative method, the first interest is that we we avoid the event of filling. That means the matrix can belong every time during the iteration of our method sparse. That means it's completely different from the direct method that we change the structure of the matrix during the method. So the other problem, the other aspect is the size of the matrix. When we have a very large size matrix, the eigen problem can't be solved by classical numerical algorithm. For example, one of the very famous and good algorithm to solve eigen problem when the size is not very large is QR algorithm. QR algorithm, the stability of this algorithm is dependent on the size of the problem. So we can't make use of this algorithm. We are obliged to define the new method. One of the new method is the projection method. So the projection method is just this chain. We have a very large space, and our eigen problem is defined in this larger space. We project the problem in a small subspace, and we solve the problem, projected problem in this small subspace to have some approximation of the initial problem. But this approximation is, we have to do some manipulation on the result of this space to have the result as an approximated solution of the initial problem. So this is just a typical iterative process. That means here we begin with a subspace, initial subspace as all iterative method. We begin with an initial condition, initial information, and we repeat the process. Our process here is this one. That means we have the projection, solution in the subspace, and we have some approximation of our solution. And if we are not happy, we re-begin the process. So this is our iterative method. So, the projection, iterative projection methods, in general, we make use of one subspace that we call Krylov method. I don't know if you know Krylov method. It's just the subspace is spanned by an initial vector, any initial vector, and after the product of our matrix to this initial vector, for example, x, ax, after a power 2x, etc. This is the Krylov vectors that span our subspace or subspace. So this is defined here. We have an initial vector, and we have this this set of Krylov vector, and this subspace is the space spanned by these vectors. So what we see here is that we begin with an initial vector. Okay, so the initial vector is choose the completely is random in the first, and after, when we have our result here, we make use of this approximate results to define a new and better initial vector. So we will have a better initial subspace. So we can continue and improve the precision of the results with time, with the iterations, and we will have hopefully good approximation in the first. So we have seen that this kind of iterative method are interesting because the sparsity is preserved, and also we can the reduction of the size of the problem. This is exactly what we use in machine learning technique to reduce the dimension of the data set. So one question that we can have here is what about the size of the subspace? We can also we can use also this parameter to have better subspaces. We will see this after. So now we know what is the iterative projection method to solve a very large eigenproblem. I would like to say what I have forgotten to say. Here, we do the projection. The projection is very time consuming because we have the matrix. We make use of the matrix of very large size here, just here. After we have to solve a small problem, for this small problem, we just need to make use of classical solution, classical methods to solve this kind of problem because the size of small or moderate. So now I would like to introduce a very innovative approach to have good convergence for the projection, the methods, projection iterative methods. So we suppose that for solving exactly the same problem, we have several projection methods. So several iterative methods. This can be projection iterative method or not, especially projection method. So we suppose that we have L methods able to solve our problem, for example, eigenproblem. So we propose to collaborate this method in order to have a global method and better convergence. So this can be defined by this chain. We have a set of each row indicate a set of iterative method, and we can make a collaborate. For example, here Pilon chose and other methods, or here Erin, etc. Here, for example, Erin, Gemres, which is another method, projection iterative method, etc. Or any other projection iterative method with the method defined as convergence accelerator. That means, we can make use of different methods to have a better convergence of overall method, method for our problem. So this can be defined by, we have, for example, L as defined here, L iterative projection method, and we can launch in parallel these methods. So that is the iterative method. So each method can iterate and improve its performance. But we decide that after each iteration, each method sends the intermediary results, its intermediary results to the other method, and the approach is symmetrical. That means each iterative method does exactly the same things. After each iteration, all the information, computed information are sent to the other commethods. And the other commethods do the same things. And that means when, for example, here, this commethod finished one iteration, if this commethod hasn't the information coming from the other commethods, so it uses its own approximated solution to rebegin another iteration. But if it has the other information, it received the other information, so it choose the best of this information and use this best of information to rebegin another iteration. So you can see very clearly that these commethods can be we can make use of coarse parallelism to implement this kind of method. The communication are asynchronous. We can have yes.
Sorry, yes.
Just for the first iteration, it's random. Yes. Yes, you know, for the first iteration is random, but for the second and all of the other iteration is the best between what each of commethod has. So, but I have to say that you know, here when we define the condition, the new condition of for restarting the process, this is a function to be defined, and this function is very important. This is the strategy of restarting, and this strategy is very a key element of this kind of method. So we can see that we have multi-level parallelism because there is coarse-grained parallelism between commethod, but inside of each method we have the parallelism, intrinsic parallelism of each of commethod, and we have communication, asynchronous communication. And what is very important in this kind of method is fault tolerant. That means if one of this commethod disappears, it's not a problem. The other commethods can continue, and also we have a great potential of dynamic load balancing. We can, in the first view, we can see that if, for example, the initial condition here imposes many data, we can put this commethod on a very important computer, and we have also many parameters. When we begin to program this kind of method, we can see that we have so many parameters that you know, now we can say that machine learning techniques can be interesting to find the optimization to optimize these parameters. So I would like to argue to the conclusion that it's not so easy to program this kind of algorithm. We need the high-level language and environment, as you know. So, you know, the synthesis, there is many publications on this, on the method that we have defined with in the context of unite and conquer. And, but this paper is a synthesis of many of them. So, I would like to say also that a particular case of the unite and conquer method is when you have exactly the same commethod, but you know, as the initial information are different, this is as we have the instances of some co-method. You know, in this case, we call this kind of method multiple method. So, for example, multiple ARM is one numerical algorithm to compute. This is a projection iterative method, explicitly restarted Arnoldi method. So, we defined many iterative methods, and for example, this one. It's a method used in embed graph of NVIDIA for clustering. And what is important to say concerning machine learning method is that this kind of method allows to do the reduction of dimension. You know, reduction of dimension of the data set. It's very important everywhere, almost everywhere in machine learning technique. So this is a good information. Another information for the case of asynchronous communication between the co-methods is that we have a certain non-determinism. We introduce non-determinism in this kind of method. You know, the numerical analyst doesn't like this kind of non-determinism. But this is in the DNA of a machine learning method. You know, all is probability. So it's the application of this kind of method in machine learning is even better than in a numerical method. So this is just to show you what is the situation for numerical application of unite and conquer. You know, here we have, for example, one method which is IRAM method. It's a method, very robust method to compute the eigenvalue of a problem. So here we have IRAM. For the case, this special case, we haven't the convergence of IRAM, but unite and conquer applied to IRAM gave us the very good convergence. And here we see also the scalability of unite and conquer, especially multiple errors. And with respect to the number of co-methods, you know, we have when we make use of more co-methods, we have a better convergence in general. So this is the result of experiments on K computer. This is many years ago, I think perhaps 6-7 years ago, and we have the convergence of multiple IRAM, which is better. Here is the convergence of 3 independent IRAM, and we haven't the convergence, but multiple IRAM have the convergence, and the chain of the time of total time with respect of the time of communication here, we can see that the time of communication is really small because it's asynchronous, you know. Okay, so I arrived to the case of to the problem of programming this kind of method. As I said, this is very difficult to program because we have so many parameters, and you know, I think we have to consider a very general programming model that with two main aspects. The first aspect is we have to respect a component approach. That means each component has to be as possible to be very independent. So that means this component approach has to apply to hardware aspects, but also on software aspects. Software aspects, that means we have to have the aspects, different aspects of software engineering, that means component approach can allow interoperability, reusability, durability, etc. But also in the hardware point of view, we can see that we have to make, to define our program in order to be possible to use it on many different architectures, heterogeneous architectures. That means we can have, in the same time, we can, if we can use of a server, a setup server, a serial computer, or other kind of computer, this will be very good. We will have a good reusability. So the second aspect of our general programming model is that we have to be able to define an application as a graph of components. So graph of components, that means each component can be itself a graph of components. And so that means the communication between the asynchronous communication has to be between the coarse-grained task, but we can have also the communication asynchronous or particularly synchronous communication between the core inside of each task, each component. So that means also that we have to be able to define, to make use of the core in very last level, but also the nodes with each node can be a setup or a single GPU, etc. So, for this programming model, this kind of programming model, again, I repeat that we need adaptive language and environment. So I can speak about YML and under your control, Pegasus. So, according to the programming model that I come to explain, this kind of environment has to have this kind of model. We have a front end, the interface with the user or programmer. We have the core of the framework, and we have to have one backend. This is interaction with the middleware or operating system when we are in a supercomputer. So the core is constituted of two parts: the integration services. That means the library, the data warehouse for intermediary results, etc., and the engine of workflow programming. So this is the architectures of YML, that is an environment implemented by our teams. And this YML is exactly adapted in, it's defined according to this model. So concerning Pegasus, this is the best chain that I find. I'm not sure that is the best. What do you think about that?
I think it's a good one.
It's not the best.
No, it is.
It is.
Yeah,
So, because the most general that I found.
The math is responsible.
Yeah, well, I'll see what you say, and we'll give you a better one.
Okay, so I see that you have DAG.
Yeah.
This is a little different with YML, because in YML we have DAG, but we have also without D. So undirected. So otherwise, I can see a very important difference, but just under your control, these concerns, Pegasus concerns distributed system. YML is in the first YML was for grid computing. After we integrated a parallel machine, and after we have both of them. But you can say more.
Yeah, I think it would be interesting to see, you know, have these to work, especially, you know, your talk kind of makes me think of federated learning, and also because you distribute various computations, and so I mean, you know, I don't know how it is applicable, but you know, with Pegasus we can distribute some of the computations, you know, to the edge and to the cloud or to an HPC. So I wonder if some of your techniques, you know, especially looking at smaller problem size and then integrate a bigger model, might be applicable in that type of context. But
so I stop there, and we will discuss after. So, but you know, I can conclude from what we have seen about high performance computing for numerical with this kind of new approach of numerical methods, and the environment that I explained that, you know, we can have the question what kind of numerical method we can have. This is just you know, the information about what we have to use. We have to use some methods, numerical or other, that avoid synchronous communication. We have to promote asynchronous communication. We have to take into account the heterogeneity of the components, etc. And you know, from this list, we can see that Unite and Conquer respond very well to this requirement. So this is the reason that I think Unite and Conquer approach is very good for this kind of environment. So I would like now to show how we can apply this kind of approach to machine learning techniques, and especially to application of machine learning. I present here just 2 examples, but initially I wanted to present 3 examples, but it's a little long. You know, I decided to present just an example in clustering, another example in cybersecurity, more especially in anomaly detection. So, you know, for the clustering, we have spectral computation and K-mean algorithm. You will see that, and as I said, our algorithm it's implemented in Emad graph of NVIDIA and used by many people. And the second example is it's Unite and Conquer for the problem of classification. That anomaly detection, it's just binary classification. And we make use of ensemble learning, which is a technique in machine learning, together with Unite and Conquer, and we defined 2 kind of framework for that, 2 kind of methods, and this one I don't present. So the first example is the clustering. You know, the clustering, for this clustering technique, I would like to say that the example is concern the purchase of books, political books, and in Amazon. And we would like to cluster the books, the buyers according to the books oriented to the right, the left, or in the center. So this is, when we have this kind of problem, we define a graph that is which represented all of the nodes into the buyer, and we would like to define a set of subset of clusters, defining, as I said, 3 groups. So there is 2 existing good methods to do that: modularity maximization and minimum balanced cut. 2 different methods. In this one, we make use of eigenproblem. In this one also, but in this one we make use of Laplacian matrix, and in this one the matrix is different. In this one we compute the smallest eigenvalue and corresponding eigenvectors. In this one we compute the largest eigenvalue and corresponding eigenvectors. So anyway, we make use of this one, and we make use of our multiple theorem. NS is for nested subspaces, and the equivalent in the symmetrical case, which is defined, which is named by this one. So, the algorithm is very simple. We have these 6 steps. We define the number of the desired cluster for our case is just 3, and we define our modularity matrix from the adjacency matrix of the graph and some vector, definite vector, and we compute the largest, the p largest eigenvalue and their this is eigenvalue and their corresponding eigenvector by the method that I presented, and after we apply one k-means algorithm to define the clusters. So we have these steps to obtain these clusters. So here we have the profiling of this technique, modularity clustering. Here is the time. So this is the first. Excuse me. Here is the eigenvalue problem. Solver takes 90% of time, of total time of the algorithm, and even in eigenvalue computation, we have the matrix, sparse matrix vector computation that takes 90% of time. So we can see the importance of eigenvalue problem here, and also matrix, sparse matrix vector multiplications. So we can see here that we have 80% of precision for our clustering technique. This is the real case, and here the result with our clustering technique. Just to say that, I would like to say that the clustering, the best clustering techniques is based on eigenvalue problem. You solve eigenproblem. What is eigenproblem is just to define the good part of, to extract the good part of data set. And the second part, the second example is about classification, binary classification, and I would like that to say that all of this kind of classification is possible, but we apply unite and conquer to for binary classification. So for that, I would like to explain that there is two ensemble learning is composed of some more basic machine learning technique. This is boosting and bagging. You know, this is bagging. That means the data set is divided in some bags, and some different machine learning method are trained on these bags. And on the end, it's just a system of voting to choose the best one. The boosting technique is we have just one bag, we apply one model, one method to this bag, and we improve the bag during the iteration with a fixed number of iteration. And in the last, we define what is the best model and best bag. The application of unite and conquer to bagging and boosting is that we define, for example, the bagging inside the boosting technique. We have many general possibility, but just this possibility define a bagging technique inside of a boosting, and we apply the unite and conquer approach in the sense of that we improve the result in the end of each iteration. We begin with the result, intermediate result, improving the intermediate results are used to define some new bag and model, and to boost this model again and again up to obtaining the good precision. So just some results. Here we have an example of anomaly detection with our technique. We have the precision here. This is the number of iteration, and we have the boosted graph curve method, and we see the best. This is very better than this one. Here we have just 4 anomaly detection technique, but this is the application of unite and conquer on this anomaly detection technique, and we see the results are really more better. And so I can not represent that, but this is just experiments in parallel, but we have some problem from here because you know the communication are synchronous in this version, and we can see that this situation is not very good. That means asynchronous version could solve this kind of problem. And the last curve of performance is when we have bagging in boosting, but 2 or several chain of this bagging in boosting, and all of this bagging and boosting cooperate to improve the result. So this is a very spectacular result in the sense that we have 100% of precision. You know, this is the precision, very, very rapidly we have the precision. And the rate of misclassification with the test data set, you know, the data set that has never been seen by the model, it's very good, you know. We have, this is the rate, that is the number percent of misclassification. So I would like to finish here with this concluding remarks that the generality of aspects of unite and conquer approach. That means we are not obliged to make use of unite and conquer just in numerical algorithm, numerical method, nor in machine learning. It's the approach is very, very general, and we can apply it to any iterative method, set of iterative method. And but I would like to say that this approach is a good approach, but especially that eigen problem is very important on high performance learning. And we have to be careful to don't use every time the call to the function, because when we call the function, we don't think about innovation concerning the method that we use, and also the interaction. It's there is many interactions between linear algebra problem and machine learning, and we have to study again these interactions, and all of this together with adaptation to the emerging supercomputers and making use of good environment, high-level environment and high-level language. And what is very important is to save our data. Every experiment that we do now, we have to do it carefully, very clean by saving input, output, and all kind of data, because many things depend on the experiments that we have done, and the ideas come after. The ideas how we can optimize the parameter of our problem. So that is, thank you.
Great, thank you so much. Online as well, so maybe I'll ask the people online first if they have any questions, and you can type your question in, or you can unmute yourself and ask live. I'm thinking, is there a question from the audience?
This one?
Yes.
Oh.
Yeah.
Sorry. Oh. This one?
Yes, yeah, that was the one. Yeah. So on the graph.
You would like to say that, for example, this one is one node of the graph?
Yeah.
Yes.
That's the way.
We can consider that in this manner. This one is a node. This one is on another node, but it's not obligatory to have the nodes of the same weight.
And very large. One of these processes communicate with another one. communication between.
Can I go to you?
Yes, of course.
So, for example, if you have now the number 1, number 2, and number 3, number L. Okay, so this is the graph is this form, for example, is not the best. But we have, for example, a node alpha, which define the just. I try to have the good representation of. It's not. It's not
Centralized.
just one of the method that we use is to dedicate one node to receive all the information from the other. So, it's depend of what kind of programming we want to do. One kind is this one. We send information everywhere. Every node send information here, and this is this dedicated node. It's receive all information in asynchronous way, and after when one node would like to repeat its work, now in the same node, I'm in the same node. I make use of the information, the last information, the updated information there. I choose the best, and the best is sent here. This is not very good figure because this is the same, exactly the same. So I have the information here, the updated information here, and I can re-begin another iteration.
You could just have a central.
Yes, yes.
But
Okay, so all right, so then this.
each node, each method.
Sure. Each of the node is very large program.
So thank you so much.
Thank you.